Section: Introduction. In this section, we delve into the exploration of language model (LLM) mechanisms through circuits. Circuits are computational subgraphs that elucidate how LLMs solve tasks. These circuits can be identified and validated using various methods to uncover the algorithms used by the models to solve tasks. It is important to note that while much of the research on circuits focuses on LLMs, the context in which this research is conducted often differs from that of models currently in use. Most LLM circuits are analyzed at the end of pre-training, whereas deployed models undergo continuous training or fine-tuning for specific tasks. Previous studies have examined model development during training, but there is limited research on LLM mechanisms. Our study aims to fill this gap by investigating when and how circuits and their components emerge during training, and whether they remain consistent across different training stages and model sizes. We conducted our analysis on models from the Pythia suite, ranging from 70 million to 2.8 billion parameters, and supplemented our findings with data from models up to 12 billion parameters. Our results indicate a remarkable consistency in the emergence of circuits and their components across various model scales and training stages. We observed that the acquisition of task-solving abilities and the emergence of functional components occur at similar points across different model sizes. For instance, components like name mover heads and copy suppression heads consistently emerge at comparable stages across different scales. This aligns with previous findings that induction heads typically emerge around 2 billion to 5 billion tokens across models of all sizes. Furthermore, our analysis of the indirect object identification (IOI) circuit revealed that the overall algorithm remains stable even when individual components change. This suggests a level of algorithmic stability across different model scales, indicating that certain circuits may generalize well, especially for simpler tasks. Our findings imply that circuit analysis can be effective across various training stages and model sizes, even when there are fluctuations in component and circuit sizes. In summary, our study demonstrates that circuit analysis can generalize effectively over different training stages and model scales, suggesting that insights gained from studying circuits in smaller models at the end of training can be informative for larger models with longer training runs. We look forward to further validating these findings for more complex circuits, reinforcing the robustness of our initial results. Section Summary. In this section, we explore the emergence of circuits in large language models, LLMs, during training and across different scales. We find that task ability acquisition rates and the emergence of functional components like name mover heads are consistent across various model sizes. Our results suggest that circuit analysis can generalize well over training and scale, even with component and circuit size changes, indicating stability in the algorithms used by LLMs. Section: Circuit Finding. In this section, we explore how we can find accurate circuits efficiently across multiple checkpoints using attribution-based methods. These methods help us evaluate the importance of connections in a model's graph without being influenced by the model's size. Among various attribution methods, we opt for edge attribution patching with integrated gradients, EAPIG, due to its reliability in finding faithful circuits. EAPIG assesses the significance of each edge by approximating how the loss would change if that edge was altered. By performing a fixed number of integrated gradient steps, typically 5, EAPIG scores all edges in the model. We then construct our circuit by selecting the edges with the highest scores, aiming to achieve at least 80% of the model's overall performance. We apply this method to the Pythia model suite, which consists of autoregressive language models with different training checkpoints. These models range from 70 million to 12 billion parameters and are trained on a substantial amount of data. We focus on simple tasks to understand how these models operate, such as indirect object identification and gendered pronoun tasks. For instance, in the indirect object identification task, we analyze how models prioritize between different entities in a sentence. Similarly, in the gendered pronoun task, we investigate the gender associations made by the models when referring to specific individuals. By studying these tasks and analyzing the circuits identified by our method, we aim to gain insights into the inner workings of these language models. Our approach allows us to uncover key nodes and structures within the models, providing a deeper understanding of their functionality. Section Summary. In this section, we utilize efficient attribution-based circuit finding methods to identify faithful circuits in large-scale models across multiple checkpoints. By selecting edge attribution patching with integrated gradients, EAPIG, we can accurately score the importance of model edges using a gradient-based approach, resulting in more faithful circuits with fewer edges. These circuits are defined by greedily selecting edges with the highest scores, aiming to capture key model mechanisms while acknowledging the challenge of ensuring complete circuit comprehensiveness. Section: Greater than. In this section, we explore the greater than task, which evaluates a model's ability to complete inputs by predicting valid years. For example, if the input is, the war lasted from the year 1732 to the year 17, the model needs to predict a year greater than 32. We measure task performance using probability difference, which compares the probabilities of valid years, from 33 to 99, versus invalid years, from 00 to 32. In the subject-verb agreement, SVA, task, models predict verb forms that match the subject of a sentence. For instance, given the input, the keys on the cabinet, the model should predict are instead of is. We measure model performance by comparing the probabilities assigned to verbs that agree with the subject versus those that do not. To analyze how language models, LLMs, behave on these tasks over time, we run each model on each task. Our results show three main trends across all tasks. Firstly, most models reach similar task performance levels by the end of training, except for the weakest model. Secondly, once models start learning a task, their performance generally improves or remains stable, with minor fluctuations. Thirdly, there is a limit to how much larger models benefit from increased scale in learning tasks. Performance tends to plateau. We then investigate the emergence of specific components within the models that are crucial for task performance. These components include induction heads, successor heads, copy suppression heads, and name mover heads, which play key roles in tasks like IOI and greater than. By analyzing the behavior of these components over time, we can understand how they contribute to the model's task learning trends. Section Summary. In this section, we measure model performance on the greater than task by evaluating the probability difference when predicting valid years in given inputs. We also analyze subject-verb agreement tasks and observe trends in model behavior and performance across various tasks, highlighting the emergence of specific attention head components that contribute to task learning. Section: Algorithmic stability and generalizability in post-formation circuits. In this section, we showed that across different tasks, models of various sizes can learn to perform the task equally well after the same amount of training. This is because each task relies on components that develop after a similar number of training tokens across models. However, we also noticed that certain attention heads can change their function over the course of training. This leads us to ask, if the heads used to solve a task change, does the algorithm used by the model change as well? And how well do these algorithms work across different model sizes? To delve deeper into how the behaviors of model components change during training, we focused on examining the components in one specific model, Pythia 160 meters, over the training period. By studying the top 5 heads in Pythia 160 meters that exhibit a particular behavior, we found that the identity of components in each circuit is not fixed over time. Some components may stop exhibiting certain behaviors or switch roles during training. Despite these changes, the model's performance on tasks remains stable, possibly due to a self-repair mechanism that helps maintain behavioral consistency. We then explored whether changes in attention heads participating in a circuit lead to alterations in the underlying algorithm. By analyzing the IOI circuit, a well-understood circuit in our set of tasks, we reverse-engineered its algorithm at the end of training. We developed metrics to assess if the model continued to follow this algorithm and found that the algorithm remained stable throughout training once the initial circuit was formed. This stability was observed across different model sizes, indicating that the model's performance is consistent even when individual components change roles. Overall, our findings suggest that the algorithms in fully pre-trained models remain stable despite shifts in component behaviors. While some components may stop playing their roles, other components can adapt and take on new responsibilities without significantly altering the algorithm. This adaptability allows the model to maintain performance on tasks even as components evolve. Additionally, our analysis indicates that these algorithmic similarities hold across different model scales, with minor variations in the specific components involved. Section Summary. In this section, we explore the stability and generalizability of algorithms in post-formation circuits. We observe that attention heads in models can change their function over time, prompting questions about how these changes affect the underlying algorithms and their generalization across different model scales. Despite fluctuations in individual circuit components, our analysis reveals that the core algorithmic behavior remains stable once the initial circuit is formed, suggesting that these circuits can adapt to component shifts without significantly altering the overall algorithm. Section: Implications for Interpretability Research. In this section, we explored the implications of our findings for interpretability research. Our study focused on a limited set of circuits but has significant implications for understanding how models evolve over time. We found that analyzing models at different points during training can offer insights into earlier and later phases of training. Additionally, studying smaller models can sometimes provide valuable insights applicable to larger models, reducing the computational burden of interpretability research. However, it is essential to conduct further research across a broader range of tasks and model architectures to confirm these trends. Our analysis was constrained to tasks feasible for small models, limiting the scope of our claims. Future work should explore more complex tasks that may show different trends. It is also crucial to study models from various model families to understand if our results are specific to the Pythia model family we examined. Moreover, our analysis only focused on circuits during training, while open-source models are often fine-tuned, which could lead to different changes in mechanisms. Future research should delve into more complex phenomena, such as self-repair and load-balancing mechanisms in large language models, to ensure consistent task performance despite component fluctuations. We also discussed the interpretability of language models over time, highlighting the importance of mechanistic interpretability in understanding neural networks. By studying the stability and generalizability of language model circuits and components, we aim to enhance the safety and reliability of AI systems by identifying and mitigating harmful patterns. Our contribution to the field of mechanistic interpretability lies in advancing the understanding of how mechanisms remain relevant across training and model scale. This knowledge can assist in detecting critical behaviors in language models, ultimately improving the safety and reliability of AI systems.